everybody. My name is Alberto Marquez, and this is a video on queuing theory. This is the video number 3 in the series, and I am going to discuss how to solve a few problems. Let's consider the first problem as a GG1, that it's we do not know if the inter-arrival process has a specific distribution or the processing time has another distribution. We are not sure about that, but we are able to observe that the average arrival rate is 4 customers per hour. We know that the service time is on average we can process 6 customers per hour, and we can observe that the average number of clients in the queue is 5. So what are the performance indicators that we can compute using this information? First, we can compute the average waiting time in the line, exclusively in the line, and for that we use Little's law, which is the relation of W and L based on using the parameter lambda, the inter-arrival rate. So we have in this particular example, LQ is 5 and lambda is 4. So the average waiting time in line is 1 hour and 15 minutes, 1.25 hours. We can also compute the total time expected to be in the system, which would be the total time in the queue plus the time that we would expect to spend at the server. That is 5 divided by 4 for the waiting time plus 1/6 in the service or in the server. And that yields a total of 1.41 hours. We can also compute the utilization, what percentage of the time the server is busy. In this case, only one server is busy 66% of the time. How many clients do we find in the server? On average, we find 66, because every time that the server is busy, it's holding one customer, and when it's not busy, it's not having any customers. So on average is 66 clients at any given time, and therefore LL, the total number of clients in the system, would be 5.66. So this is GG1. Let's consider a more specific MM1. In this example, let's consider an ice cream parlor with 1 worker. The arrivals are 10 customers per hour following a Poisson distribution. That means that it's an exponential inter-arrival times. So Poisson counts the number of arrivals per time, and the exponential then, when the number of arrivals is Poisson, then the inter-arrival times follow an exponential distribution. So the service time is 4 minutes per customer, also following an exponential. And the questions that we have is, what is the probability of having a queue? What is the average queue length? What is the average time of a customer in the system? And if the worker likes to study for his engineering courses and he can study 6 pages per hour, how many pages can he or she study in an hour while working on the job, while working on this parlor? First, let's consider the data that we have. We know that lambda is 10 per hour, and we know that mu is 15 per hour. So we can compute the probability of having a queue as 1 minus P0 minus P1. Why? Because P0 is the probability of having absolutely no customers in the system, and P1 is the probability of having exactly 1 customer in the system. And in those 2 circumstances, we don't have a queue, because when we have 1 customer, that customer is at the server and we don't have anybody in the queue. So the probability of having a queue starts with P2. So 1 minus P0 minus P1 is all the other options from 2 to infinity, and that number is 0.444. How did I find that number? Well, first, we know that rho is lambda divided by mu, which is 2/3 or 0.666. From that, we can compute the probability of having 0 clients, which is 1 minus rho, because rho is the utilization, and that means that P0 is, when it's not being used, is the opposite of, or the complementary of the balance of the time, which is P0, and then that's 0.33. And there is a formula that we can use to compute the probability of having 1 client, which is rho to the 1 times P0, and that's 0.666 times 0.333, that's 0.222, and when we do the computations of 1 minus P0 minus P1, we'll obtain 0.44. The average queue length can be computed using the formula for LQ, since we already have rho, as rho squared divided by 1 minus rho, and that yields 1.333 clients on average. Remember, these are averages. And since the utilization is 0.66, then the number of clients with when we have only one client, one server, is also 0.666, and therefore the total number in the system is 2. The average time of a customer in the system is how long it spends both in the queue and in the server. We have a formula for that that is very simple: 1 divided by mu minus lambda, and in this example that will be 1/5, which is 0.2 hours, which is 12 minutes. Finally, answering the question about how many pages can this worker make progress on his studies. If he reads and studies 6 pages per hour in normal conditions, and he is idle 1/3 of the time, because P0 equals 1/3, then he can make progress on 1/3 times 6, which is equal to 2 pages per hour. Very good. That is the computations for the MM1. Now let's consider an MMC. This is an interesting problem in my opinion. We have a calibration station that requires technicians. The technicians are there to repair or calibrate these equipment, and the number of equipment that arrive are 12 equipments per hour. The service time is exponential, with an average of 8 minutes per equipment. And the technicians make $160 per day. And equipment revenue lost is $300 per day. The question is, how many technicians is optimal to have? So let's see how can we answer that. So since we want to know how many technicians we need, we can start with evaluating the minimum number of technicians needed, or that are feasible. If we wanted to have 1 technician and the service time being exponential with an average of 8 minutes per each one of the items, that means that we can only process 7.5 items per hour, and the arrival is 12 per hour. That means that we will receive more than we can process if we would only have 1 technician. So that means that the MM1 is not feasible. We cannot have only 1 technician. If we use the formulas to compute the number of entities in the system, number of clients in the system, we can compute rho for the MM2 as 80% when we have 2 clients, or I'm sorry, 2 servers, and the expected number of items in the system as to be repaired or calibrated is 4.44, and the total number of items in the servers on average would be 1.6. We can repeat these computations for a few more options. If I do it for the MM3, the row will be 53.3, and that's the utilization. Since I have more servers, the number of items to be calibrated in the system drops from 4.44 to 1.91, and the total number of items in the system remains 1.6. If I increase the number of servers to 4, now the value of row, the utilization drops to 40%. The total number of items in the system drops to 1.66, and the number of items in the server is 1.6. Finally, MM5 with the 5 servers, the utilization drops to 32%, and the number of items to be repaired drops to 1.61, with most of them, 1.6 of them, being at the server. Only a few of them will be at the queue. So now I use that information to estimate my cost. So the cost of the MM2, if I have 4.44 items to be repaired and I lose revenue of $300 for every day that I don't use that item, that is 4.44 times $300 plus the 2 technicians that I need to operate that system at $160 each, yields a total of $1,653. In a similar fashion, I can compute the cost for operating with 3 technicians, since the number of items to be repaired in the system drops to 1.91, and the number of technicians increases to 3. After doing the computations for the cost, now the cost has been reduced to $1,053.87. I compute the next alternative, which includes 4 operators, and what we can see is that the number of items in the system drops to 1.66, and the number of technicians increases to 4, but the decrease in the cost due to the fact that we have less equipment pending to be fixed do not compensate for adding another technician, and the overall cost actually increases from 1,053 in the previous option to now 1,138. Finally, the computation for the alternative with 5 servers, the number of items pending to be fixed reduces even more to 1.61 to 1, but that does not compensate for the additional technician, and the total cost is 1,653. So clearly the optimal option is to having 3 servers in the system. And that concludes this video. I hope you see the benefit and the potential of learning more about queuing theory. As you can see, it is very helpful for the estimation of the optimal level of operations in this type of environment, and the potential is huge. Of course, there are limitations, and that's why we will study simulation as well.